Hello, everyone. It's me, Billy Younger, again from www.youtube.com/Billy with a capital B, Younger with a capital Y, Physics with a capital P, Solutions with a capital S. I am going to show you another Gauss's law problem. This one again is spherical, but it's a little tougher, and then I've given you a charge density that is the actual function of position. So we're going to actually do an integral for the right-hand side of Gauss's law. So that's sort of the part that makes it moderately more difficult, but really is still fairly trivial. And you can find ways around doing the actual integral, but I figured what the heck, we'll just go ahead and show it. I will be making use of a differential volume element that's 4 pi r squared dr, and you might want to look in my YouTube channel. There is a video called explaining why our differential volume elements formulas appear weird. So that explains actually why it's not a 4/3 pi parentheses r plus dr close parentheses cubed minus 4/3 pi r cubed. So anyways, that might come in handy. Let me start off by showing you the actual problem. So let me share screen. So here's the problem I have imagined for you. It is a non-conducting sphere of radius big R and total charge big Q. Again, we're on this going on the assumption that we know those. Has a charge density of rho equals alpha times R, where alpha is a constant and R is the distance from the center of the sphere to any specific point within the sphere. Notice alpha is something we don't know. Given that we know the radius of the total charge sphere, compute alpha and tell us what units it would have in the SI. So that's part of what we're going to do. Part B, compute the electric field caused by this field by the sphere for R less than big R, in other words, inside of the sphere. And then C, compute the electric field for the sphere caused by the sphere for R greater than big R, and graph its magnitude for all R. I said, note, if the sphere center is at the origin, then R is the spherical coordinate R, which is always the distance from the origin. It has a unit vector R hat that at any point points away from the origin, but along the line connecting the point to the origin. So that's just again, me re-expressing how nice it is to use a symbol with a name R hat just to specify a direction. So hopefully everybody's got that. I've copied it to some sense into my iPad GoodNotes. So let's stop this share and let's begin sharing my iPad. So I'm going to share my iPad document, which you can see now. And okay, hold on, just stopped again. Let me fix that. Okay, there you go. So a non-conducting sphere of radius big R and total charge big Q has a charge per unit volume rho equals alpha R, where R is a constant and R is the distance from the center of the sphere to any point in it. What I want to find in A is alpha, and I mean it and its units. What I want to find in B is E for R less than R. And what I want to find in C is E for R greater than R. So again, this is a Gauss's law problem. I will start off by writing the solution. Whoa. Let's start off by writing solution. Okay, now given the spherical symmetry of this whole situation, again, I'm leaning towards the electric field being E of R times R hat. I'm thinking in terms of a Gaussian surface that would be spherical and so on and so forth. So I'm going to go ahead and say part one. Or actually, I shouldn't say part one yet. I should figure out what alpha is first. So we'll do A. So I'll just call that A. What we know is Q, the charge they gave us, is equal to the integral of rho dV. That's sort of the definition of charge if you're given a rho. If you were given a sigma, it'd be integral of sigma dA. If you were given a lambda, it'd be the integral of lambda dL. So in this case, what I'm going to do is I'll pull that alpha out in front because we know that's a constant. And I'm going to say rho is just alpha times R. I've already handled the alpha. And for a sphere, I'm going to say the differential volume element, because remember when you're integrating to get like an area or volume or something, the integrand can't change by more than an infinitesimal amount, i.e. a differential amount, over the body of the differential element, or else you'll have to do some averaging process. So since the variable that we're dealing with is r, I can't let r change by more than, say, dr. So what I'm going to use for my differential volume element is, in fact, I'm going to imagine that a sphere has a surface area of 4 pi r squared, and that if I multiply that by dr, I'll get the volume of a thick one. Obviously, that's a little bit off, but again, you can look up, probably just do a search for the word differential on my YouTube channel, and you'll find my explanation. But it's 4 pi r squared dr is what I'm integrating from over, and I want to integrate from r equals 0 to big R. Okay. So we can see in this case, we're going to get Q is equal to 4 pi alpha times the integral of r cubed dr from 0 to big R. The integral of r cubed, of course, is r to the 4th divided by 4. So that gets rid of my 4 out in front. So I'll just call this pi alpha. And then it's going to be big R to the 4th minus 0 to the 4th. So I just want to say r to the 4th. Now I know that's what Q is. So this immediately tells me that alpha is equal to Q over pi times r to the 4th. That's what alpha is. I will box it off with a nice blue box, and you can probably tell from that in fact the units of alpha, or the dimensions, whatever you want to say, the units of alpha is going to be, in fact, coulombs per meter to the 4th power. And that too is exactly right. So now we know what alpha is. If I knew the total charge Q numerically and R numerically, I can put those in and get an actual number for alpha. So I've done part A. Part B, this is where I'm going to use Gauss's law, and I'm going to start by drawing a coordinate system again. And what we're doing is we're calling this the x-axis, this the y-axis, and this the z-axis. I'm going to, in fact, assume my sphere is green. That is the worst looking sphere ever. Ran right off the side of my board. Okay, that gave me a pretty good sphere after I let the program correct it. So that's the sphere that we're actually integrating over. And in fact, it has a radius of big R. And in fact, you could draw this right here to make sure everybody can tell that it's actual sphere. Now I'm going to choose a Gaussian surface because of the spherical symmetry of the situation. We know our hypothesis is that E is equal to some E of R pointing in the R hat direction, and this is the R hat direction according to spherical coordinates, not cylindrical coordinates. In other words, it has the I, J, and K component, not just I and J. More stuff falling off of my desk. Don't know where they're coming from, but they're clearly trying to kill me. Anyways, now that I have that, I'm going to do part B, which is left-hand side. So the left-hand side of Gauss's law is the closed integral of E dot dA. Okay, in order to do that, I need my Gaussian surface. I haven't drawn that yet, so I'm going to draw it now. That was supposed to be my Gaussian surface, but it did not correct for my horrible drawing, so I'm drawing it again. Much better that time. Okay. Still not that happy with it. In fact, I'm gonna try to move it a little bit so I can get it sort of centered. Okay, that looks pretty good. And now I'm going to say that this radius is lowercase r. Again, I can draw some dots around here to show that it's actually a sphere. Again, I can consider a little patch on the sphere here with the dA vector being dA r hat. So what I end up getting on the Gaussian surface, I end up getting an integral on the Gaussian surface of E of r hat dotted with dA r hat, which becomes E of r integral dA r hat dot r hat, which, as I told you before, if you're doing Gauss's law and you end up having to do any kind of weird integrals or anything, instead of just getting E times some area, then you've done it horribly wrong. So r hat dot r hat. Jeez. Everything just fell for no reason. Sorry about that, everybody. That was kind of neat little scenario. I'm wondering if my floor falling through or what. But anyways, in integrating the integral of E of r dA, the E of r, since it's on a radius r that's a constant, that comes out in front, and I just get E of r times 4 pi r squared, where r is the radius of the Gaussian surface, lowercase r that is, and that is of course smaller than big R. Now the right hand side is a little bit of a problem. So the right hand side, I'm going to write it again. Right hand side is equal to Q enclosed over epsilon naught. So I'm going to say that's 1 over epsilon naught, and I'm going to say it's equal to the integral of rho dV, where I'm going to integrate from 0 to r less than big R. This is going to pan out the exact same way that my integral did before. I'm going to get a 4 pi alpha coming out in front, but this time, of course, I have a 1 over epsilon 0, so I got to take care of that. And I'm going to integrate r to the third power dr from r equals 0 to little r. And of course, this is going to make 1/4 r to the 4th. So the 4 is going to cancel out, and I'm going to get pi times alpha over epsilon naught times r to the 4th power. And that's what the right hand side is. So setting left hand side equal to right hand side, I get E of r times 4 pi r squared is equal to pi alpha over epsilon naught r to the 4th. But before I do that, I can't have this answer in terms of alpha. I've got to actually submit my alpha. So I'm going to say E of r times 4 pi r squared is equal to pi r to the 4th over epsilon naught, and then all that times q over pi r to the 4th with a big R. So the reason I do that, you see, is that ultimately I'll just have answers in terms of things that I already know, specifically Q and big R. So this pi is going to cancel out with this pi, and in fact, 2 of these is going to cancel out with all of that, which I'll put an X through like that. So ultimately, you see what's going to happen is that I get E. Oops, I don't want to use that color. I'm going to get E, the vector, is equal to Q over 4 pi epsilon naught Now I have the r to the fourth, the big R to the fourth, that is, in the bottom. And in fact, in the top, I just have a r to the fourth. Actually, r to the fourth canceled out with two of those. So I'm left with r squared on the top. And all of this will point in the r hat direction. And this is for r less than big R. Okay. So in this case, you see that unlike the uniformly distributed charge case, where the electric field was linear from R equals 0 to big R, in this case, it's actually quadratic. And that's because the farther you get out, the larger the amount of charge per cubic, say, millimeter, because rho is literally equal to some constant times R. So now I can do part B, and part B is supposed to be for R greater than big R, excuse me. So let's get started on that. Oops, I don't know what happened here. Oh, I went to the wrong document. Sorry about that. Okay, so we'll start on part B. So part B is for R greater than big R. And what you'll see is because there's no surface charge, it's going to be a continuous thing. So I can actually make it greater than or equal to and less than or equal to in both cases. Now I'm doing a Gaussian surface that's actually bigger than R. So I will try to do it as neatly as possible. And that looks pretty good. Again, this radius now is little r. Which is greater than big R. Okay. Again, we still have the same little patch somewhere and a dA vector, which is just dA times r hat. So the left-hand side, oops. So the left-hand side is actually super easy. The closed integral of E dot dA. It's the same problem we did before. It's just E of R times 4 pi R squared. And the right-hand side is quite easy too. The right-hand side says that it's Q enclosed over epsilon naught. Well, we know that that new sphere actually encloses the entire sphere. So this is just Q over epsilon naught. So we get that E is equal to just Q over 4 pi epsilon naught R squared R hat. And that's for R greater than R equal to big R. Because if you notice, if you put big R in for little r in the expression in part A, you'll get exactly the same thing as you get here. So I'm trying to box this off so you can see the final answer. And now if we want to make an actual plot of this magnitude as a function of position, what I'll do is I will make a little black coordinate system. It'll go from here to say here. That's R and that's E. And I apologize for it splitting up my Gauss's law part. But anyways, what we know it's going to be right here is Q over 4 pi epsilon naught R squared. Right here, it'll be big R. And what we're going to get, at least from this particular problem, is this is going to go like a parabola to that. And then from there, it's going to fall off like 1 over R squared. So this is proportional to 1 over R squared. And that's what the magnitude of the electric field will actually look like as a function of position. I apologize for it being so small, but luckily that's the beauty of technology. We can zoom in on it all we want right here and say, oh, wow, that's a really good looking graph, Mr. Younger. So anyways, we have that. That's definitely a 4 pi there. Let me make that a little clearer now that I'm in this small frame. Okay, what this is supposed to be is Q over 4 pi epsilon naught big R squared. And then, of course, what this is over here is supposed to be, it's just a box. So I now can zoom this back down and see what it is. So that's it. That's a quote unquote more complicated version of Gauss's law. And really the only thing that made it more complicated was the fact that I had a charge distribution that depended on R. You could make it depend on theta, you could make it depend on phi. The integrals might not work out so nicely there. So I have found that it works fine for rho equals some constant times R, rho equals some constant times R squared, rho equals some constant times R cubed, all that stuff. You can use those if you want. They all work, but really that's yet another example of Gauss's law. I apologize. I'm just noticing how non-radial my second dA vector looks for the second Gaussian surface. But anyways, I think you get the picture. I hope you all have a good day and tell a friend. Bye-bye.